Okay, so today's Tuesday, February 7th, calculating acceleration. I can calculate acceleration, right? So objects that are standing still or moving straight lines at a constant speed are pretty easy to understand. In the real world, though, objects change speeds and the directions all the time. You have heard people refer to as different speeds and directions using terms like acceleration, deceleration, or going backwards. So we're going to start by taking a look at how we calculate that. Get the speaker notes here. Calculating acceleration. This young child is accelerating, believe it or not. Changing direction is part of acceleration. Before we can understand how and why objects move, we must first understand that motion, what motion is. Think of sitting in a moving car. What does acceleration feel like? How do you know you are accelerating? All right. Which image shows negative acceleration? So remember, negative acceleration is slowing down, or what we commonly call as deceleration. So the van is decelerating. An object accelerating backwards is just moving in a different direction. This is acceleration. So going backwards is backwards accelerating, forward accelerating, or slowing down are all accelerations, and then changing directions is acceleration. Acceleration is the change in velocity over time. Velocity is an object's speed in a certain direction. Ask yourself, if an object changes direction, does the velocity change? If its velocity is changing, then we are calling that acceleration. Acceleration can occur anytime an object changes how fast it's moving, but velocity includes direction, so an object changes in direction even if it doesn't change in speed. Acceleration is the change in velocity over time, so direction has a big part of it. Speeding up is positive acceleration. Change in direction, you can feel this acceleration as you turn the corner of a car. Your body is being pushed toward the outside of the car. Speeding up, you can feel your body being pushed back. Slowing down, negative acceleration. You can feel your body being pulled forward. The speed of the horses of a carousel is constant, but the horses are accelerating because of the changing constantly. The direction's changing constantly. Is this dog accelerating? Sure. All right. I'm accelerating because I'm speeding up, and you can see these stick figures. They're spread apart, so they're closer together, and as they move further to the right, there's more distance between them. I'm accelerating because I'm speeding up. I'm accelerating because I'm slowing down. You can see that I'm further apart, and then I get closer and closer. I'm accelerating because I'm changing directions. Calculating acceleration, to calculate acceleration of an object, the change in the velocity is divided by the length of time over which the change occurred. To calculate this, we need the initial velocity and we subtract that from the final velocity. That's the change in velocity over the time interval. So here we are, ending velocity minus starting velocity over time. So looks very similar to the triangle we've used for distance. We just have A for acceleration. We covered this up. And then you've got your VF minus V1 VI divided by the time. When you go signal, when the go signal is given, you take 5 seconds to get your maximum sprinting speed of 5.4 meters per second. What is your acceleration in meters per second squared? All right, so the acceleration here, 5.4 meters minus your 0, and then we're dividing it by 1.08 seconds. So what is your acceleration? So 1.8 meters per second. And then we divide this into 5. So we've got 5. We're going to move this over 2. Move this over 2. So 40. So 5 meters per second squared. If I did that right, I hope so. Suppose a jetliner starts at rest, the end of a runway, and reaches a speed of 80 meters per second in 20 seconds. What's the acceleration? So again, it's 80 minus 0 divided by 20. So this is meters per second. So my velocity is 80 meters per second divided by 20 seconds. That's why we get the second squared. So we get 4 meters per second, or 4 meters per second squared. For every second, it's changing its acceleration by 4 meters. It's getting faster and faster and faster, but at a constant rate. So 0 is my, break it down for you. 0 is my initial, 80 is my final. So 80 minus 0. So to find the change in velocity, which is correct, we're going to choose this one. Clicked on it accidentally. So velocity final minus velocity initial. All right, so we already calculated this. All right, negative acceleration. The skateboarder is moving south at a speed of 36 meters per second and comes to a stop in 6 seconds. What is the starting velocity? And what's my final velocity? So final velocity is 0, my starting velocity is 36 meters per second. So 0 minus 36 gives us negative 36 divided by 6. So we got a negative 6 meters per second squared. Units of acceleration. So acceleration of the is can be thought of as meters per second squared, miles per hour squared, feet per second squared, kilometers per hour squared. So let's take a look at the yellow car. Goes from 0 meters initial to final 29 meters. Both these cars do the same thing, but the yellow car takes 10 seconds, so it gets 2.9 meters per second, but the red fast car, I'm not sure it's a Corvette, 7.3 meters per second, takes less time. Which are units of acceleration? Here we are, meters per second squared. What is the acceleration of a hockey player skating 10 meters per second and comes to a complete stop in 2 seconds? So this is going to be a negative one because we started at 0, our initial velocity was 10 meters per second. So this is the final minus the initial, and we're going to divide by 2. So negative 10 divided by 2, this is meters per second, divided by second. So it's going to be negative 5 meters per second squared. All right, any questions?